Chapter 5, Run-off River Types of Hydropower Projects. 5.1 General layout of components in a typical power plant, dam body, weir, spillway, under sluices and intakes with examples. 5.1.1 Component parts of hydropower project intake arrangement of structures situated at the entrance of the canals or tunnel or pipes through which withdraws water from the river, pond or reservoir and conveyed to the powerhouse to produce electricity. Reservoir. The main purpose of the reservoir is to store water during rainy season and supply the same during the dry season, and thus it helps in supplying water to the turbines according to the load. Supply conduits. It supply water from intake structures to forebay or surge tank. The supply conduits might be canal, pipe, tunnel or combination of these. Non-pressure flow is generally occurring in supply conduits. There may be low pressure flow at the river/stream crossing in superpassage/siphon/aqueduct. Forebay. It is an enlarged section of power canal just upstream of penstock. It is required only when the conveyance system is of channel flow. Surge tank. When conveyance system consists of pressure tunnel, a surge tank is usually required at the upstream of penstock. The surge tank helps in stabilizing the velocity and pressure in the penstock and also reduces the water hammer effect. Penstock. It is the pipe that supply water from the head pond, reservoir, forebay or surge tank to the turbine of powerhouse at high pressure. It is a part of water conveyance system where pressurized flow occurs. Wall thickness should be enough to withstand surge pressure. 94. Casing. It is a structural arrangement provided in around the turbine runner to control and guide the flow with minimum head loss and to control the splashing of flow after striking the runner. Casing design depends on the types of turbines used in powerhouse. Impulse turbine. Flowing fluid energy is converted into kinetic energy through nozzle jet flow before striking the runner. The free jet impinges on the series of bucket of the runner, causing rotation of the runner in air. Casing is provided only for control of splashing water, and there will be no fluid pressure for the casing. Reactive turbine. Only a part of available energy of flowing water is converted into the kinetic energy and substantial part remains in pressure energy. Water flows through the specially designed spiral casing and enter the turbine tangentially to rotate the runner due to high pressure flow. The spiral casing is the winding duct of varying size with opening on the runner side. The casing should be smooth to minimize the head loss. The thickness of the casing should be sufficient to bear the high pressure. Draft tube. The draft tubes are either straight conical draft tubes with a circular section, or they are elbow-shaped tubes with gradually increasing area. The shape is changing from circular at the runner section to rectangular at the outlet section. The draft tubes are needed only for reactive turbine to fulfill the following functions. Achieve the recovery of the velocity head at the runner outlet, which otherwise would have gone to waste, as exit loss permits the turbine to be installed at higher level than the tail water level, which facilitate the maintenance of the turbine. A conduit which connects the outlet of a reaction turbine runner to the tail race. Hydrocone. It is the central solid cone provided in the draft tube to achieve eddy free flow so that the head loss between the draft tube inlet and outlet is minimized. 95. Tail race. The channel through which water is discharged back to the river after running the turbines. The outlet level of the tail race channel should be at higher than the flood level of the stream. There should avoid excessive silting and scouring of the tail race channel bed. If the powerhouse is close to the stream, the outflow may be discharged directly into the stream. Plan and section of diversion canal plant. 5.2 Different types of intakes, importance, location and types. Design concepts of intake structure, head loss calculation in intake structure, trash rack losses. 5.2.1 Intake. It is a hydraulic structure constructed at the head of an irrigation canal, tunnel conduit, or power canal to obtain the required quantity of water from the river or reservoir for the different engineering purposes. 96. 5.2.2 Purposes of intake. The main purposes of intake structure as a regulating structure are follows: to admit and regulate water from the source and possibly to meter the flow rate. To control the sediment entry into canal, to admit smooth, easy, and turbulence-free entry of water into the canal. To prevent the clogging of the entrance with floating debris. The following are major appurtenances of the intake structure: the raised inlet sill to prevent entry of the bedload of the river. The skimmer wall at the inlet to trap floating ice and debris. The trash rack equipped with either manual or automatic power-driven rack cleaning devices. The settling basin followed by an entrance sill diverting the sediment layer towards the flushing canal. The flushing sluice to flush the deposited silt. The intake gates to control the flow rate into canal. The scouring sluices in the diversion were to flush the bed load upstream of the inlet sill. Trash rack of Chaco HP and trash rack of Panati HP. 5.2.3 Location of intake. The river reach upstream of the intake should be well established with stable banks. The best location for the intake is the outer, concave, bank to avoid bed load with the intake located toward the downstream end of the bend. The structure should be aligned to produce a suitable curvature of flow into the intake, and a diversion angle of around 300 to 450 is usually recommended to produce curvature of flow. 97. 5.2.4 Types of intake based on location. Surface intake, side intake, frontal intake, drop intake, Himalayan intake. Subsurface intake, power or 4-bay intake, tower intake. Based on hydraulic features: runoff river intake, canal intake, dam intake, tower intake, shaft intake. Runoff river intake. It is provided for runoff river plants and form an integral part of the powerhouse. It is having a bell-mouthed entrance covered with trash rack. A control valve is usually located just downstream of the entrance. In silty rivers, special arrangement for the desilting are usually 98. Constructed upstream of the intake. Side intake, frontal intake, Himalayan intake, and drop intake are under the runoff river intake. Reservoir intake, dam intake, tower intake, and shaft intake are under the categories of reservoir intake. Dam intake, generally for the powerhouse located at the toe of the dam. Such type of intake structure is suitable. It is suitable when topography supports the foundation for dam. In case of valley dam plants, this type of intake is suited in the body of the dam. Dam intake. 99. Tower intake. Tower intakes are normally on hillsides, not far off from the dam, when it is not convenient to provide other type of intake directly on the U/S face of the dam. They are also constructed when there is a large discharge or wide fluctuation of water level. Flow into the intake occurs through ports provided at different levels. Tower intake. Shaft intake. It is vertical or nearly vertical shaft driven into the bed of the river at the reservoir site to supply water to the tunnel or penstock feeding the powerhouse. 5.2.5 Losses in intake. The intake losses include entrance losses, rack losses, and head loss. Entrance losses. The entrance losses comprise: the loss due to change in direction of flow is given by H equals -C, where V velocity in the canal, VF velocity of flow in the main stream. 100. C constant depends on an angle of diversion and ranging between 0.8 to 0.4. Coefficient C has higher values for intakes with lower offtake angles and lower values for 900 diversions. The loss due to sudden contraction of an area at the diversion. The loss is equivalent. H equals K, where K varies between 0.03 for round-mouthed entry to 1.3 for sharp entry. Rack losses. Widely used formula is Kirchner's formula, H equals K/sin empty set, where H rack losses K. A factor depends on the cross-section of bar T, thickness of rack bar B, spacing between bars VB, velocity of flow in front of bars, angle of bar with the horizontal. Head losses. The gate contract the flow. The coefficient CD in the following formula: Q equals CD A2GH, where Q flow in conduit A, area of gate opening H, difference in head acting on the gate CD, coefficient of discharge, CD equals 0.62, 0.83. 5.2.6 Design concept of intake. Decide suitable type of intake based on site and hydraulic conditions and consider the following velocity. 101. Approach velocity 1 meter per second. Trash rack 0.6 to 0.75 m/s. Intake gate 1 to 2 m/s. Decide number of opening of intake. Account for contraction effect due to abutment or piers. Calculate hydraulic losses. e.g. head loss due to trash rack, entrance loss, transition loss, gate loss, exit loss. Ensure no entry of air. The system can trap air due to the formation of vortex due to hydraulic jump condition, submergence, velocity at intake, etc. Ensure the release of trapped air to avoid formation of vacuum cavities inside the system by providing inlet aeration facilities such as air vent. 5.3 Performance standards of headwork, control of bed load and floating debris in intakes, Himalayan intakes, and hydraulic design of gravel trap. One of the major functions of the intake is to minimize the amount of debris and sediment carried by the incoming water. So to avoid the entry of these particles into intake and obtain relatively clean water, various structures are made at headwork. Some of them are explained below. Trash rack is placed at the entrance to the intake to prevent the entry of floating debris and large stones. A trash rack is made up of one or more panels, fabricated from a series of evenly spaced parallel metal bars. Trash racks are fabricated with stainless steel or plastic bars. Undersluice. The undersluice is provided to flush out the sediments deposited in front of the intake and thus control the bed levels in its approach area. The undersluice shall be designed as a broad-crested RoR with downstream submergence. Normally, energy dissipation downstream of the undersluice shall be achieved through stilling basin. Gravel trap. The gravel trap is constructed close to the intake in order to prevent gravel from getting into the approach canal. Main function of the gravel trap is to collect the bed load. 102. Smaller than the trash rack opening size, entering through the canal. Gravel trap is generally designed to collect maximum of 12 hours gravel deposit. A flushing arrangement associated with the gravel trap is operated to flush out the collected gravels to the river. Gravel trap. Hydraulic design of gravel trap. Hydraulic design of gravel trap is very similar to that of settling basin design. Critical velocity. The critical velocity of flow for the size of gravels to be transported shall be determined by V equals a square root d, where A equals coefficient depends on particle size, d equals average particle size. Length of gravel trap based on the flow velocity in the trap and the settling time of the particle. The length of settling trap shall be obtained as L equals Tv. Here, Td is time of detention, which is equal to the time of settling, thus T equals H omega. Hence, lengths of the gravel trap, L, equals here, omega is settling velocity. Flushing velocity. The flushing velocity in the trap gallery may be found out by formula, V equals 2gh. Here, phi is coefficient of velocity. Flushing time. 103. The time taken for flushing, emptying, volume of water and gravel mixture from the gravel trap will be determined as T equals here, VO equals volume of water gravel mixture, QF equals flushing discharge. 5.3.1 Himalayan intake. Himalayan intake is a special type of intake that has proper system for management of both floating debris and bed load. It was invented by H. Stoll in 1996. The geometric design of an intake structure is to be used in runoff river hydropower intake in steep Himalayan rivers. Main purpose of Himalayan intake is to maintain a reservoir volume for daily peaking by providing means of flushing of sediments from reservoir. The intake is designed to function in a river which carries both floating debris and large amount of coarse sediments, including sizes up to rocks and boulders. 5.4 Sediment handling measures, types, location and design criteria of settling basin, its design and estimation of sediment volume. 5.4.1 Parameters of settling basin design. Settling velocity, W. The settling velocity of a sediment particle is defined as the rate at which the sediment settles in still fluid. For fully turbulent condition, d greater than 1 mm, omega equals 3.33 GD increment, here, increment equals gamma minus gamma, / gamma W. For transition flow condition, 0.1 mm d less than 1 mm, omega equals increment, here, C equals plus 0.34. For laminar flow condition, d less than 0.1 mm, omega equals, here, C equals where, omega equals setting velocity, d equals particle size diameter, CD equals coefficient of drag, Re equals Reynolds number, V equals kinematic viscosity coefficient of water, G equals specific gravity of particle. 104. 5.4.2 Design Criteria of the Settling Basin. The design of a settling basin aims to meet the following criteria: to determine maximum size of particle 2 mm escaped from the gravel trap, to determine total sediment load to the turbines, to optimize sediment exclusion with respect to cost parameters, to use the available length, and to manage with as minimum width as possible depending on the topography and intake location, to secure high generation regularity. Ideal settling basin. Ideal basin. Settling time, Ts, equals I. Detention time, Td, equals 2. Where omega equals settling velocity, fall velocity, v equals horizontal velocity, flow velocity, for quiescent liquid all particles of settling velocity, omega, are removed when detention time equal to settling time equals. Omega equals. The ratio can be regarded as a dimensionless indicator of the physical ability of a basin. Of surface area A to remove particles of fall velocity omega at supplied discharge Q. The ratio termed as surface loading. 105. Settling basin, Kudi HP. Settling basin, Sunkoshi SHP. Real settling basin. In order to satisfy the requirement for good hydraulic performance, the basin is divided into three main zones: inlet zone, settling zone, outlet zone. 106. Settling basin. Inlet zone. The inlet is used to gradually decrease microturbulence and avoid secondary current by decreasing the flow velocity. It helps to distribute the flow uniformly over the vertical cross-section. Thus, the channel is gradually expansion in 110. Vertical slope AR entrance at inlet zone is 1:2 and there will be submerged weir. Settling zone. It is a main part of the basin. The effective length is considered to be 85% of its uniform length and minimum basin length is 4 to 6 times of width. Critical velocity of flow is taken as 0.25 to 0.5 meters per second. The depth of settling tank is 3 to 5.5 m and longitudinal slope of the tank is 150 to 120. The dead storage depth is 20 to 25% of whole depth of flow. From operational point of view, the basin is divided into at least 2 chambers with a longitudinal wall instead of constructing a long and narrow size basin. Outlet zone. Outlet zone is provided to facilities getting back the flow into conveyance system. It should not hinder the settling of suspended sediment. It helps to controls the water level in the basin. The outlet transition is generally taken as 260 and velocity of flushing gallery is considered as 2 to 3.5 meters per second. The minimum flushing frequency is 3 to 4 days and flushing discharge is considered as 10 to 30% of design discharge. 107. Typical L-section and cross-section of the settling basin. 5.4.3 Design principle of a settling basin. Particle approach flushing discharge. The flushing discharge should be capable of inducing bed load movement. Usually flushing discharge range from 10 to 30% of the intake discharge. Velocity in the basin. E. Mosoni suggested that desirable range of 0.4 to 0.6 meters per second. However, such a velocity means greater length stilling basins, often leading to uneconomical sizes. A velocity of up to 0.35 meters per second can be considered. According to T.R. Camp, the critical velocity, i.e. limiting flow-through velocity, can be determined by the relation v equals a square root d, I, where v flow-through velocity m/s. 108. Deep diameter of particle up to which sediment load is desired to be removed in MMA, constant, which is 0.36 for d 1 mm, 0.44 for 1 mm, d greater than 0.1 mm, 0.51 for d less than 0.1 mm. However, R.S. Varshney, 1985, recommended the following coefficient for Himalayan rivers: 0.55 for d 1 mm, 0.66 for 1 mm, d greater than 0.1 mm, 0.77 for d less than 0.1 mm. Size of sediment load to be removed. The effort should be made to remove as much silt load, consequently as low fraction of sediment load as economically and hydraulically possible. The latest practice is to eliminate sediment particles up to 0.15 to 0.2 mm size. Dimension of settling basin: if the depth of basin is h, width b, flow-through velocity v, then discharge passing through the basin is q equals b.h.v. 2. If omega is the settling velocity, the settling time t equals 3. The length of the basin is governed by the consideration that water particles entering the basin and the sediment particles conveyed by them with equal horizontal velocity, i.e. flow-through velocity v, only reach the end of the basin after a period longer than the settling time. Thus retention period should not be shorter than settling time. The required length of basin is thus L equals V.T, 4, from equation 3, and, for L omega equals H.V. Obviously a solution of the problem is not possible unless 4, Q, omega V, H, of the 6 parameters, Q, omega V, H, L, and B, are known. The 3 parameters Q, omega V are already decided. H can be selected, thus length and breadth can be determined by the equation 2, and V, respectively. Table: fall velocity of suspended sediment. 109. Particle size dmm, fall velocity in cm/s, water temperature 0 C, settling velocity for quartz 00 C, particles in cm/s, 150 C, 400 C, 0.05, 0.13, 0.20, 0.30, 0.20, 0.10, 0.5, 0.7, 1.2, 0.7, 0.15, 1.00, 1.50, 2.00, 1.7, 0.2, 1.7, 2.13. 0.02, 0.30, 0.25, 2.13, 0.04, 3.00, 0.33, 0.004, 0.005, 0.003, 0.80, 0.44, 0.205, 0.306, 0.505.0, adopted from the curve given by Hunter Rouse in Engineering Hydraulics. With consider to the retarding effect of turbulent flow on subsiding particles, settling is lower in flowing water. Mosonier recommended a lower settling velocity omega minus omega, where omega is the reduction due to turbulence. L. Levin has given relation for omega as below: omega equals alpha v. 6. Alpha may be found as alpha equals dot square root 7. Then, settling length I, L equals dot 8. Where h, depths of water in sedimentation chamber, m, omega, fall velocity obtained from table 5.2, and rugosity coefficient equals 0.013 v, mean velocity of flow in m/sl, length of settling basin in mb, width of settling basin in mq, discharge passing through intake in m3/xc, quantity of sediment of given particle size in effluent qs, quantity of sediment of given particle size in influent. Concentration approach: in this method, the basin is designed to achieve desired trapping efficiency. Various combination of depth, width and length can be considered to achieve the desired efficiency. There are various methods for concentration approach. 110. Camp's method. In this method, trapping efficiency is function of dimensionless parameter with U** and with /q, where U* is the shear velocity. Shear velocity is given as U** operator equals gr, where I equals frictional slope equals. Once, with U* is computed, with /q for certain value of trap efficiency can be obtained. For known value of W and Q, as can be calculated. Camp's chart. Vetter's method for the given value of W and Q, as can be calculated directly using the formulae. Eta equals 1 minus E. Hazen's method. Eta equals 1 minus m omega v. The parameter is used to quantify performance of the settling basin, where m equals 0 represents best performance, and m equals 1 represents very poor performance. Design steps of concentration method assume removal of the sediment particle to 90% to 95% efficiency. 111. After assuming efficiency, calculate AS using Vetter's equation or using Camp's chart. Assume length to breadth of the basin equals 4 to 10. Length and breadth can be calculated. Calculate depth of the basin using continuity equation. Q equals AV, estimation of sediment volume, weight of the sediment equals Q*T*C, where Q equals discharge, T equals detention time, C equals concentration. Velikanov's formula. The empirical formula for determination of the length of the settling basin is given by Velikanov. It is especially used to check the length of the basin calculated from the analytical method. The necessary settling length for turbulent flow is computed from settling velocity and flow velocity as L equals lambda v square root h minus 0.2. 7.51 omega, where lambda depends upon removal ratio omega. Omega denotes the ratio of settled sediment to the total load. Entering the value of lambda for given removal ratio can be calculated from the curve below. Velikanov's chart. 112. 5.4.4 Different types of settling basin. Conventional type: the basin is dewatered when it is taken out of operation. Sediments may be removed manually or with mechanical equipment after the basin is dewatered. Generally, two settling chambers are constructed so that one can still be operated while other is closed for flushing. Hooper-type water level and water flow is maintained in the basin throughout the flushing period in order to facilitate continuous power generation. Removal of sediments while the basin is operational may be achieved with continuous or intermittent flushing or by use of some kind of suction or dredging device. 113. Berry type. In berry type, the shutter mechanism in the bottom of the basin is made of two plates with series of opening. One plate is fixed while other can be moved horizontally. Flushing is done when opening in both plates falls together. Sensor can be placed at the bottom of the plate so as to sense the volume of sediment deposited in the chamber. Once the sediment collected increases the desired level of deposition, one plate is moved over the other to match the opening and sediment is flushed. S4, Serpent Sediment Sluicing System. This is a new type of descending basin which was developed by Håkon Ståhl at the Norwegian Institute of Science and Technology. It consists of a flushing channel and a flexible pipe called serpent. This pipe can float or sink in water depending upon the fluid filled inside it. When the serpent is filled with heavy fluid, it settles and flushing canal is closed and sediment is deposited over it. When the deposition reaches a limit, the fluid in pipe is removed and light gas is installed which facilitates floating of serpent and hence sediments are flushed through flushing channel. 114. Hydrocyclone particles in a hydrocyclone are trapped due to centrifugal action. When the head of the power plant is significant, several 100 m, very fine particles have to be removed. Conventional gravity basin for such purpose is usually not feasible due to unavailability of space and cost. Hydrocyclones are suitable and efficient for such purpose. 5.5 Flushing of settling basin. Flushing frequency, periodical and continuous. Based on flushing mechanism, settling basin can be classified into two groups. 5.5.1 Continuous flushing type. These types of basin are designed with hoppers. The settled particles pass through the bottom of the hoppers to the collecting channel and are flushed continuously. Continuous flushing descending basin uses surplus water for flushing, i.e. about 10% of plant discharge. These type of settling basins do not interfere power production during flushing process. The design and operation of continuous type settling basin is complex compared to discontinuous type. The main problem is clogging of the sediment extracting system. Example: hopper type and hydrocyclone. 5.5.2 Discontinuous flushing type. In this type of settling basin, sediments are not flushed continuously. In this type of flushing, descending basin are of much simpler in design and are much less susceptible to clogging. The main operating convenience is that plant output should be cut back for multi-basin or shut down for single basin. In first phase, the suspended sediments are allowed to settle in the settling zone. In second phase, the deposited sediments are removed by different systems. They are further classified into two classes. Periodic flushing type. In this type of settling basin, power plant is shut down during flushing. Flushing is generally done by conventional gravity flushing method. Mechanical removal, dredging, is also another means of sediment removal. If other means turn out to be inefficient, the settling basin should be cleaned by manually removing the sediments. Example: conventional type settling basin. 115. Intermittent flushing type. In this type of settling basin, flushing is not continuous. However, power plant is not shut down during flushing. Flushing is done at regular intervals and the power generation is done continuously. Example: berry type and S4 type.